Let's start our lectures. Lecture 1, Introductions. So in these lectures, we are going to, first of all, we are going to talk about what's the thermodynamics and what's the difference between the thermodynamics and kinetics. And in the second part, we are going to talk about equilibrium state. Equilibrium state actually is defined in thermodynamics. And the other important part is what is the steady state. Always talk about in kinetics process. So we are going to talk about what's the steady state and what's the difference between the equilibrium state in thermodynamics and the steady state in kinetics process. And steady state, actually, you can consider that as a steady flow process. It's a flow process. So kinetics process always is a steady flow process. And this is what we are talking about in this class. The third part, we are going to talk about flow process. So how to quantitatively describe flow process. So flow means definitely in this system there exists some driving force, right? So because of the driving force, so you got the flux driven by the driving force. Then that will accompany with some entropy production. So in these sections, we are going to teach you how to describe quantitatively the flow process by using these beautiful equations. And in these equations, we link the driving force, corresponding flux, and accompanying associated entropy production rate at working temperature. So there's the equation here, and this equation can well describe the flow process. And at the end of these sections, we are going to talk about how about if in your interesting system there are two or more driving forces exist. How to calculate and how these different forces affect the corresponding flux. For example, that if your materials, like thermoelectric materials, there are two driving forces coexist in apply on these materials. The first one will be the electrical field. So this driving force will drive what? What kind of flux driven by the electrical field? Would be the current density. And besides the electrical field, there are the other driving force we call the temperature gradient or thermal gradient apply on these materials. So this driving force will cause the what kind of flux? Will be the heat flux. So the point is here. Does the electrical field affect the heat flow? Then, does the temperature gradient or thermal gradient affect the current density? Then we are going to talk about this in the last section of these lectures. So this is a coupling of the forces and corresponding flux. And actually the answer would be yes. There's a coupling coefficient exists here. That means the electrical field applied on this material will cause the current. Yes. But this electrical field will also affect the heat flow. Similarly, the temperature gradient will cause the heat flow, but it also will affect the current density. So the detail will be introduced in the last section of these lectures. Okay, so let's move to the first part, thermodynamics and kinetics. So we are going to give you a brief review of thermodynamics and starting from the laws of thermodynamics. The first law of thermodynamics is we call the energy conservation law. This law states that if now we have a system or a body, the heat observed by this body will be equal the internal energy of the body plus the work done by the body. So this is, we call it is the energy conservation law. And this law also states that just tell you we can transfer, the energy transformation is okay. You can transfer, the energy can be transferred to different kind of energy. For example, like you can transfer the heat, the thermal energy to internal energy or the mechanical work, but you cannot create energy. So the transformation of energy is okay, but you cannot create the energy from nowhere. And the second law is we call the entropy, is related to entropy, right? Okay, so this is the heat related to the heat flow in and out of the system, and the work here in thermodynamics we always usually talk about would be the mechanical work, P times dV, and here the heat flow in and out of the system will be related to the second law. So what's the second law? Tell you is the entropy law, right? It tell you that it introduces the term we call the entropy. So the heat exchange at a constant temperature will result in the change in entropy. So that tell you this second law tell you can predict the direction of your system by calculate the entropy. If it is a reversible process, the change of entropy will be equals to 0. And if the entropy is larger than 0, that means the entropy the change of entropy is positive. That means this process is irreversible, spontaneous process. So the entropy cannot, the change in entropy cannot be, could never be negative. So by calculate the change of entropy or change in entropy, then you can predict the direction of your interesting process is irreversible, reversible, or is impossible. Irreversible means the change in entropy is larger, is positive. Reversible is like the change in entropy is equals to 0, and impossible means after calculations, the change in entropy is negative. So you can say, oh, this process is impossible. I mean, never happened. Okay, so by simply combine the first law and the second law, then you got the equation like this. The change of the internal energy can be equals to the heat T times ds minus the mechanical work part is the P, the pressure, times the change of volume of the system. So you got this one. And this we also call it is energy state function, one of the energy state function. Based on this, we also, in thermodynamics, it also introduce you the other three state function, energy state function, right? Included this is the internal energy, and will be the enthalpy, Helmholtz energy A, and the Gibbs free energy G. And the one important assumption by using this energy state function would be, so far the energy state function, this du, the change of internal energy, equals to T ds minus P dV. This equation, combined from first law and second law, can only be applied in what? In a closed system with fixed size and also the fixed composition. Okay, so now we have other three energy. So can we get the energy state function here? Yes, you can just simply, for example, like dH, for the enthalpy part, you can just you can deviate it. So it's a dH equals du plus P dV and the V dP. And here du, you also know, you already get that is equals to T ds minus P dV. And you just copy the rest of it, then drop the same atom here. So you got the dH, the change of enthalpy equals to T ds plus V dP. So the enthalpy, the change of enthalpy is related to the heat and also the mechanical work, right, by the system. And use the same technique, you can get the dA equals to minus the SDT minus P dV, and dG Gibbs free energy, the change of Gibbs free energy equals to minus entropy dt plus volume dP. So now we have 4 energy state function. And remember, these 4 energy state function can be only used in the closed system with fixed size and composition. But some people probably will ask, in solid state or in chemical reactions, in material systems, during your synthesis, the composition of our materials sometimes changed. Because, for example, like the chemical reaction, you react your reactant A and B, then probably you will get the C and D. That means the composition changed in your material system. So how to deal with this kind of system? We cannot directly use this energy state function, right? Because this can only be used in fixed composition. So we do need to do some modifications on this energy state function. So this slide just shows you the variation. If our system have some variations of the composition and size, what we can do here. So we take the Gibbs free energy as an example. So the energy state function, Gibbs free energy, is dependent with temperature, pressure, and different kinds of atoms. So that means when you change the temperature, pressure, or composition in your system, then the Gibbs free energy, this state function, will change as well. So we can get this. Equations. Du, the change of Gibbs free energy, can be written as partial G partial T dt, and the rest of parameter need to be fixed. So we get a constant P, Ni, Nj, and so on. And plus what? Plus partial G partial P dP, we change the pressure. Then the rest of parameters need to be fixed. So at constant T, Ni, Nj, and so on. So we got this equations. And as we know, if Ni, Nj remain constant during the process, then you got this, right? dG equals to minus SDT plus VdP is this one. you derive from these slides. You will compare this stuff, then the rest of it you can written. This equation can be written as this: is minus SDT 加 VDP plus VDP plus this term. This term actually is this term. Is partial G, partial Ni, dNi, and the rest of parameter need to be fixed at constant T, P, and Nj, and so on. So that means when the numbers of I atom change, that also affect the Gibbs free energy. And here we define the chemical potential of the species I. This is mu I. So what's the mu I? Chemical potential of species I means when you ended one atom, Ni atom, at constant T and P, the energy, the total energy of this system will increase. How much it increase? Then we call it, this is corresponding to the chemical potential of species I. So if you now you have not only I atom, you also have a J, K, Lm atom. You need to sum up. So we got like I equals to 1, then you got to K. So you sum up all the atoms together. So you get this term. So this is what we modify when if there's any variation of the composition and size of the system. So we need to end this term after the energy state function. So this is a modified term. So after this, based on the same concept, we modify the rest of energy state function, like dH. Then we also added the chemical potential term, and Helmholtz free energy dA. We also added the chemical potential term, and because the Gibbs free energy, right, the same. So now the energy state function we have here can deal with the system with some variation of composition and size. So now we can use this energy state function to our system. Because we, as a material scientist, we always deal with this, doing our process or synthesis process. The compositional size of our system always changed. Okay, so now let's put more efforts on introduce the detail of energy state function. For the internal energy here, du equals to T ds minus PdV plus this chemical potential term. So if you look at it carefully, this term TdS actually means the change of internal energy in your system is related to the heat flow in and out of the system, also minus the mechanical work by the system. And what? You need to end it up. What? Here is the chemical potential, right? And we can conclude that this term can be a non-mechanical work. This is mechanical work, but we need to end up if there's other non-mechanical work applied on this system or exist in this system, then you can end everything here in this term. So now, because we only have the variation in composition and size, so we only put the chemical potential term here. But if you list other like interfacial energy, latent heat, or geoheating stuff, other non-mechanical work exists in your system, you need to plus the rest of it. So this is if we observe the change of internal energy, then that will be related to the heat flow in and out of a system, also the mechanical work and all the non-mechanical work. This is the energy part, internal energy part. And next, enthalpy part. Mechanical scientists probably will be put more efforts or put more focus on the enthalpy because of the heat engine, right? So the change of enthalpy will be related to the heat flow in and out of a system, and also V plus VdP. This is a mechanical work, and also the rest of it will be the non-mechanical work. Here is a chemical potential term. But as a mechanical scientist, if usually the heat engine will perform in the isobaric process, that means at the constant pressure. So the dP equals to 0. So you can drop this term out. And if we also assume there's no non-mechanical work exists in your system, then you will get what if you observe the change of enthalpy will be related to the heat. Will be related to the heat flow in and out of a system. So it's a dH equals to TdS equals to dQ. So if you are a mechanical scientist, probably you will use the change. You will observe or measure the change of enthalpy. But if you are a chemical engineer, probably you are more interested in Helmholtz free energy, dA. As we mentioned, dA equals to minus SdT minus PdV plus the non-mechanical work. If you are a chemical engineer, and your process probably is performed in the isothermal process. Isothermal means at a constant temperature, so dT equals to 0, so you can drop this term out. So when you observe or measure the change of Helmholtz free energy, then you will know the You will know the mechanical work and all the non-mechanical work in your system, by your system. So this means when you measure the change of Helmholtz free energy, then you can know the total work, including the mechanical work and non-mechanical work applied by the system. And next, if you are a material scientist like me, then probably you are more interested in the Gibbs free energy. Gibbs free energy means the change of Gibbs free energy can be expressed like this, right? And in any material synthesis process, usually we will fix the temperature and the pressure, so will be the isothermal and isobaric process. That will be much easier to us to manipulate in our lab to synthesize material, right? So dT and dP will be equals to 0. So the change of Gibbs free energy is contributed from all non-mechanical work, right? So based on this, depends on what kind of boundary condition or what kind of what you are interested in, then you can choose which energy state function you are going to use. And as we mentioned, if we measure the change of Gibbs free energy, then at the constant temperature and also the constant pressure, then what you are going to know, what you are going to get. You can get this, right? And if you look carefully, dNi, what's dNi? It's the change of atom, species I atom, right? I atom. The change, the number of atom of species I will be changed. That means let's some mass transport happen in your system. So dNi is what this means, and mu I is the chemical potential of species I, right? And dNi means probably I atom you can increase, you get more numbers of atoms, or this I atom react with, converted to other atoms. So this dNi means the change of number, the change in number of I atom. So that means we can. So following slides, where we are going to put more focus on Gibbs free energy, because we successfully link this free energy with mass transport dNi. Okay, so give you a brief summary for the energy state function we just introduced to you, included the internal energy, Helmholtz enthalpy, and Helmholtz free energy and Gibbs free energy. The energy state function are changed by what? By the work, the total work, including the mechanical work and non-mechanical work done on or by the system. And also this energy state function also will change by the heat flow in and out of the system. As long as, and any reactions usually will accompany or associate with entropy generation in your systems. So what kind of energy state function you are going to use depending on the different conditions in your system. So we can we put it here is under different constraint, different boundary condition or settings of your system. And the other short summary will be if your settings, your boundary condition will be the constant pressure and constant volume and no mass transport. Constant pressure means dP equals to 0. The constant volume means dV equals to 0 and no mass transport. That means dNi equals to 0. So you can drop this term. dP equals to 0. dV equals to 0. So du, the change of internal energy, will be equals to change of enthalpy and equals to TdS, and TdS equals to dQ, the heat flow in and out of the system. And if you fix the volume, and because there's no mass transport, so you can drop all this term out. And if it is the fixed volume, so you can drop this fixed volume, or fixed volume and fixed pressure. So dA will be equals to dG, the change of Helmholtz free energy will be equals to change of Gibbs free energy and equals to minus SdT. Okay, so this is what we get. And if you are playing with constant pressure and constant temperature, then constant pressure and constant temperature, the dG Gibbs free and the change of Gibbs free energy can be directly related to the summation of chemical potential mu I times the dNi, the mass transport of species, different species, right? The summation of that. And so based on this, this is the energy state function. So any process, the purpose for any process will go to what? Minimize the total energy of the system, right? So by using this, if there's any mass transport happen, then we can, based on this energy, Gibbs free energy, we can know that the dG should be negative. Because if this process, the dG is negative, that means the total energy of total Gibbs free energy is decreased, right? And so we can use, so this dG is negative, that means this process will be a spontaneous and irreversible process. Probably some people will ask, how about if dG is positive? degree positive, if there's one process, degree is positive, that means this is the total system, the total energy of the system increase is impossible, right? So we can use a DG to identify the direction of your interesting reactions. Based on what? We need to calculate the DG, and we know the DG, if the DG is negative, and the direction you propose or predict is the right direction for the system. On the contrary, if DG is positive, that means your proposed direction of this reaction is not going to happen. It's impossible. It's an impossible reaction. Okay, and the other condition, probably is the other condition will be, how about the constant volume and constant temperature? Constant volume and constant temperature, and we can use the Helmholtz. You can observe the Helmholtz free energy is related to the chemical potential turn and also the mass transport. So if your system, your boundary condition or your system is at constant volume and temperature, we can use the change of Helmholtz free energy to predict the direction, the reaction direction of your reactions, because the total energy should be decreased, right? So dA should be negative. Then, if after calculation, if the dA is negative, that means your proposed direction is correct. Yeah. Okay, so we already finished. Give you a quick review of the thermodynamics. Then move to the important part is. Then just move back. How to. After introduce you lots of energy state function, so I would like to ask you how to describe a material system. Because we are material scientists, so probably the most important thing to us is, can you describe your material system by what? So some people probably will say, oh, okay, I can describe my material system by composition. Probably and the phase probably is a BCC, FCC, alpha beta phase, pressure, temperature, charge states, and some defects. All these parameters can help us to describe a material system. But the thermodynamic state, what's the relationship between the material system and thermodynamic? A thermodynamic state is a function in the multi-dimensional space. This means F is the thermodynamic state function. This thermodynamic state function can be changed by different parameters, including this N1, N2, N3, N4 can be the composition, pressure, temperature, charge state, or something. So F means the thermodynamic state function. So let's take, for example, to describe a material system, first thing come up from your mind probably is the phase diagram. So I show you this binary phase diagram of lead and tin. And expressed by what? Expressed by the temperature as a vertical axis and the weight, or you can call it a composition, as a horizontal axis. So this is a binary phase diagram. And each point shown in this phase diagram, we can call it is a thermodynamic equilibrium state. So in this by binary phase diagram, if I want you to describe the state of these materials, because you need to describe material system, right? Probably I will say, oh, there's an interesting point here. At 183 degrees C, at roughly 16.3 tin, weight percent of tin. There's an interesting point here. We call it as a leutetic point. Can you describe the state at this leutetic point? Yes, probably you will say, oh, yes, is at 183 degrees C. Is the temperature, right? And also you will describe that, the composition will be like 63% of tin. And pressure, probably this is 1 atm. And the phase here will be, there's 3 different phases coexist at this point, included the liquid phase, alpha phase, and beta phase. Alpha phase is the lead-rich phase, and the beta phase is the tin-rich phase. So at this point, there are 3 different phases coexist. So actually, I use all the parameters to try to describe this states in our materials. So this is how we describe a material, right? You use lots of parameters to try to describe this state. But just remember, this state definitely is equilibrium state, thermodynamic equilibrium state. So how about if we want you to describe the other state? For example, like is a lead, and 33% of tin at 200 degrees C probably is here. So can you describe it well? Yes, probably will say, oh, it's temperature here, and position here, and now the phase is liquid phase. Right, and you also describe the pressure for the, probably is 1 atm, something like that. And if we drop the temperature to 100 degrees C, now the phase will becomes to alpha and beta phase, right? And use the level rule, you also can calculate the composition, or how much alpha phase exists in this system materials, or how much beta phase exists in this system at this state. So here, in order to summarize everything, so we will say probably use the energy state function will be the suitable indicator to describe a material system and process. Instead of, because why we try to use the energy state function, you can think that no matter what kind of process or what kind of material systems, there must be the equilibrium, thermodynamic equilibrium state must be the lowest energy, total energy, must with the lowest energy, right? So if we use the energy state function, then it's much easier to us to determine if the state you are interested in is the lowest state and with the lowest energy or not. So this is what we want to say in this slide. Is just please probably use the energy state function. Energy state function would be a suitable way to describe a thermodynamic equilibrium state. I mean, describe your material system. And this energy state will change with what? With the composition, phase, pressure, temperature, and so on. So this F, probably we can use the energy state function will be a suitable indicator to describe our material system. Okay. And then when we finish this part, then we need to tell you more precisely what's the difference between the thermodynamics and kinetics. So we start from the thermodynamics first. As we mentioned, thermodynamics always acts talking about under the equilibrium condition. Equilibrium condition only. So now if we have 1, 2, 3, 4, 5, 6 states, and each state you can see the pressure, temperature, and the composition will be slightly different between different states. And these states we label on these 6 states is defined you can predict the state functions of material system by thermodynamics equilibrium, thermodynamics. And because this is state and defined by the thermodynamic equilibrium, that also tell you this state function doesn't change with time. Because equilibrium, right? So tell you the state function, for example, like energy state function or any state function does not change with time. Under this assumption, we call it this equilibrium state. So equilibrium state just tell you the state function do not change with time. This 1, 2, 3, 4, 5, 6 state function do not change with time. So, but if I want to move from state 1 to state 6, although the state won't change with time, right? But if I want to move in our system, if I want to move from state 1 to state 6, what we can do here? You can choose either from 1 to state 3, then move to state 6, or you want to choose state 1, move to state 4, then move to state 6, right? But finally, this is the start point, and this is the end point. So this thermodynamics help you to define the state, because your state do not change with time. But kinetics just tell you what's the kinetics. Kinetics focus on which path you choose and what's the rate by choosing that path. So in kinetics process, first of all, you need to define your start and ending point. Then you need to decide how to reach the end point what kind of path you choose to reach the end point. And then you need to calculate by choosing this path. So this is kinetics. This is also how we deal with the kinetics. First of all, you need to use the thermodynamics to predict the state first. Then you need to decide the path. You need to decide your path. How to get the state 6. Then you need to calculate the corresponding rate in this kinetics process. Okay. So this is the ideal pattern. So I'll give you some real case. For example, if we take the ideal gas as our examples, ideal gas. Ideal gas always obey the ideal gas law, right? PV equals to nRT. So when we adjust the P, the pressure, or the volume, then the numbers of atom or the temperature of the gas will be changed in the same time, right? So we use this ideal gas law to define what? Define the state. So each state 1, 4, 6, it must obey the PV equals to nRT. So as long as we know the P1, V1, then you know the N1 and T1, something like that, right? So use this ideal gas law to define the state 1, 4, and 6. So this is what we call it, like we use the thermodynamics equilibrium to predict or define our states. And these states do not change with time, because PV equals to nRT always, the ideal gas always need to obey, right? And what's the kinetics want to know is if I choose this path from 1, 4 to reach 6, during this process, I want to know the heat flow in and out of a system and also the mass transfer. So this is what kinetics deal with. During this process, kinetics process, I want to know how fast to reach state 6. And during this process, the change of number of the atoms and also how much heat flow in and out of the system. Okay, so this is the example for tell you the relationship between the thermodynamics and kinetics. Okay, so let's give you a short summary of thermodynamics. Thermodynamics actually provided you a baseline to describe the state of your material system under equilibrium conditions. And we can use the different energy functions to define different states of your system and under different conditions or boundary conditions or different constraints. Because different conditions probably there's some variations in pressure, temperature, and composition of your system. And when the system reach equilibrium, must have some like criteria or something like that. Is first of all is no spatial variation in chemical potential. No spatial variation in chemical potential. So that means in space, that everywhere, the chemical potential are the same in everywhere. Based on this, so there's no mass transfer. And the total free energy must be minimized. And minimized, that means if there's any movement will raise the free energy of the system. So no spatial variation in chemical potential. So if you draw a picture, something like that, if the vertical axis is the chemical potential and the x-axis, the horizontal axis will be the location in space. And if you draw these kind of pictures, then the curve will be the flat. That means the atoms locate at anywhere with the same chemical potential. So there's no reason there's no mass transfer because the atoms locate, they have the same energy. So there's no reason to them to like have any mass transfer, net mass transfer. Some people probably will ask, the atom always move, so no mass transfer is a little bit weird. Yes, the atom always jump in and out, jump to right, jump to left. I mean, there is no net mass transfer. That means how many? Probably is 3 atoms jump to right. Then there are 3 atoms jump to left. So you sum it up, there's no net mass transfer. Okay, so probably there's no net mass transfer would be much suitable.